Today we are going to be doing homework 2, part C, and step 1 of this homework is to derive the time-dependent heat diffusion equation for a uniform linear bar. So we can start out by drawing our uniform linear bar, and it will be divided into a number of sections. And just focusing on one section, we know that there is a flow rate coming in, and there's also a flow rate going out. So our net flow, Q net, is equal to Q in minus Q out. But we can also look at this as point 1 and point 2 having a certain distance between each other, the distance between position 1 and position 2. So if we define position 1 as being at point X, then at position 2, that would be equal to X plus delta X. So we can rewrite this be Qx minus Q of X plus delta X. And we can also rewrite this term to be Q of X plus the change in the flow rate with respect to the position times that change in position. So if we sub this in for that part of the equation, we get Q net equals Qx minus Qx plus the change in the flow rate with respect to position times that change in position. And so if you notice here, these two terms cancel. So we are left with Q net equals the negative change in the flow rate with respect to the position times this change in position. So now we can apply Fourier's law. And so if we rewrite it using Fourier's law, it will look like the negative change with respect to x of negative Ka times the change in temperature with respect to or position times dx. And so this is essentially replacing Q. And this A is our cross-sectional area because the heat is flowing through this bar, not only the position or the distance between each position, but it's flowing through that. So it's volumetric because it's being multiplied by this change in position right there. And so this is one of the main equations we'll be using in this problem. And now we can look at the overall flow. Call that Q. So our overall flow is equal to our density times our heat capacity times our change in X, or this change in position here, multiplied by our cross-sectional area, because again, it's going to be volumetric because the heat is flowing through. It's not just in one X direction, it's also Y and Z. So, and then we also need our temperature dependence, or our overall temperature, which is dependent on position and time. So if we take the derivative of this equation, get dq over t to equal our density times our heat capacity times this term here, and then multiplied by our change in temperature with respect to position. So if we combine these two equations in blue, what we end up getting is our density times our heat capacity times this change in temperature over time. You'll notice these two terms, this a, the x here, they actually cancel. So on this side, we have k, which the negatives cancel out there as well. And it will be the second derivative, temperature with respect to time, or with respect to position. And so if we simplify this a little bit and we move our rho Cp to the other side, we get the change in our temperature with respect to time to be equal to K over our density times our heat capacity times this term here. And we will actually call this term alpha. So alpha is equal to K over our density times our heat capacity. And this is actually our thermal diffusivity. So if we rewrite this one more time, we get our change in temperature with respect to time to be equal to alpha times our change in temperature with respect to position twice here. And so this is our heat diffusion equation. So that is step one. So part two of this problem is to express the heat diffusion equation that we have just derived in an algebraic version via explicit differencing. So by doing this, we'll be removing the derivatives and just making it an algebraic equation. So if we redraw our uniform linear bar here, and it will have a certain number of sections. And the main section we are going to focus on is this, which we will call I. And so these other sections will be I minus 1 and I minus 2 and I plus 1 and I plus 2. So if you look at our heat diffusion equation up here, we can see that this side on the left is looking at the change in temperature with respect to time and not position. So we can redefine that side of the equation as T of n, with n being the time counter at position I, minus T of n plus 1 at position I over the change in temperature. So that represents our change in temperature with respect to time. And then we can redefine this other side over here as well. And this is looking at the change in temperature with respect to position and not time. So we're not going to be changing the time or our n variable, but we're going to be changing I. So it would be equal to, and then we still have our alpha variable there, T at position I plus 1 of n minus T at position I of n over the change in position minus the position at I time n minus the temperature at the position I minus 1 at that same time of n over the change in x. And this is all going to be over x again because we are taking the second derivative. And I did switch these terms around. It is the temperature at the time before minus the temperature at the time right now. And so what we can do to kind of simplify this a little bit is we can move this delta T to this side, and we can take these delta X's out of this of this bracketed part of the equation. So we get T, our temperature at position I at time n plus 1 minus the temperature at position I time n equal our alpha constant times our change in time divided by our change in x squared, because it's being divided twice here. And then we will have the rest of our equation, which we have two of these terms here. So that will be minus 2 times the temperature at position I and time n, and then minus T of I minus 1 at time n. And then further, we can move this term over there. So we get the temperature of position I at time n plus 1 equal to the term here. That is plus the temperature at position I at the time of n. So that is our equation. So for part 3 of this problem, we are going to be simulating the time-dependent response of this bar when it is originally set at 20 degrees Celsius and we raise and maintain one end of the bar to 40 degrees Celsius and another end of the bar to 100 degrees Celsius. And we are going to be looking at different values of R and how that affects our system. So down here, I forgot to mention in the last clip, but we are going to call this term here R. So we can remind ourselves what R is right here. R is equal to alpha times delta T divided by delta X squared. But we will define it as 0.499 for right now. And we'll be splitting this bar up into 50 sections. So our n will be equal to 50. And our temperature will be defined as, we'll define it as an array so that we can store all of these values. And it will be an n amount, 50 different sections, and they're all going to start at 20 degrees Celsius. So we will say 20. And so when we change the ends of the bars to 40 and 100 degrees, we can define the initial value in this array, so the left side of the bar to be 40, and we can define the last term to be 100. And so now we need to define every term or every temperature in between 40 and 100, or in between the left end of the bar and the right end of the bar. So now we have to define our temperature for all of the other sections. So from 1 to the last one, it's going to equal, we have this Ti here, this, so we'll write that first. So that will be the temperature at whatever iteration it is on. And then it will be plus R times, and then we'll have a big thing here. So we'll have T of the next term here, so it'll be 2 and on, and then it would be minus 2 times T of I, or 1 to negative 1, because it's T sub I, and then it will be, oh, I just noticed actually, this is supposed to be a plus, I believe. Yeah, so this is supposed to be a plus, so good thing we got that now. So we will do plus, and then it will be T to the second to last term. Is that like right? I think so. But we need this to be in a loop because we want it to plot as it goes through each section. So we will say for n in range 5,000, this will be indented. We'll calculate that, and then 5,000 is a lot, so we can have it plot like every 50 or so. So if n remainder 50 0, then we can add it to our plot. So we can say fig dot add scatter, and we haven't defined fig yet, but I will in a second. Add scatter, and then, or actually I'm going to do it now because we can't do that before. So up here I'm going to say fig equals make underscore subplots. I'll define our x-axis. It'll be a range, yeah, a range of n, because we want to see all of our 50 sections. Yeah, and so down here we can say fig dot add scatter, and then we want our x to equal our x-axis, our y to be t, mode lines, and then name, we want it to be a function of t equal to n plus 1. Oops, x-axis. And then I'm going to add another one just for our like 0 time. Fig dot add scatter. It's going to be the same pretty much except for the name. So x equals x-axis, y equals t, mode equals lines, and then name t equals 0. Full. Okay, I'm going to try just running this again, make sure that's not the problem. Okay, it's not scriptable. Okay. I did the wrong type of brackets. Okay, so now we have this. I'm not sure if like this is affecting it. Okay, so make sure you put periods there, I guess. Okay. Right, so now that this is corrected and everything looks how it's supposed to look, we can see here the temperature profiles across all 50 sections across this bar at different times. So if you see, it starts, we can look at T equals 0. You can see that basically the whole bar is still at its initial temperature of 20 degrees. And then as you go up, or as you increase your time, slowly the bar starts to heat up. And as you keep going, eventually you will get to almost a straight line from 40 to 100. All right, so now we can look at this R value up here. Right now we have it set at 0.5. So we can see what happens if we decrease it slightly. Let's do 0.499. So it looks very similar. There's not really any noticeable difference. But if you go to 0.501 maybe, you can see it becomes extremely unstable. And we will look into why that is, looking at part 4 using the von Neumann stability analysis. All right, so if we look at our main two equations here, I'll rewrite them down here. We have Ti, this one. And I'm actually going to use J's here because our solution is going to have some imaginary numbers and I don't want it to get too confusing. So I'm going to replace all the i's with j's. Unless it's an imaginary number, then it will be I. So equals r, or I'm going to put this term over here first, equals t sub j of n time, or plus r times t j plus 1 to n. Okay. And then our other main equation, our heat diffusion equation, which is alpha times temperature, and that's going to be squared. Okay. So there, for this analysis, we will have a solution of this to be e to the I k x times e to the negative alpha k squared t. So our tj of n would equal e to the I k j delta x minus, or no, e to the minus k squared. We'll have delta, or we'll have n delta t. And so for the j plus 1 value, it'd be e to the I k and then j plus 1 delta x minus, or not minus, e to the minus alpha k squared and delta t. So notice here that these two terms are the same, and the only difference here is that there's a plus 1. So we can redefine this as being equal to tj to the n, because this plus 1 right here generates this term, and it will be e to the I k delta x. And then we can do the same thing with t sub j minus 1. It will equal e to the I k j minus 1 delta x times e to the negative alpha k squared and delta t. And if we compare this to this term up here, these e terms will cancel out, and we will get t to j minus 1 equal to t j sub n e to the minus I k delta x, because it's j minus 1. So we have this term here and this term here. So now we can plug in these two equations here into our original equation up here. So I will do that to the side. We will get t j of n plus 1 equal t sub j of n plus, and then I'm just going to take the tj's out right here so it's a little simpler. Yeah, plus tjn times r of our j or tj plus 1 value, which is right here, and we took this part out, so it'll just be e to the I k delta x. And then our next term right here, since we factored the tjn out, it'll just be minus 2. And then we'll do plus this last term here, which is down here, which will be e to the negative I k delta x. And we know this identity of e to the I k delta x plus e to the minus I k delta x over 2 actually equals cosine of k delta x. So we can plug this into the equation up here. I'll just rewrite all of this, which will stay the same. And we have 2 cosine k delta x minus 2. And then I'm also just going to make this simplified a little bit. It'll be tjn, and then it'll be multiplied by 1 plus r, so we can get rid of this right here, of 2 cosine k delta x minus 2. Okay. And then this is where the von Neumann stability analysis comes in. So if we look at just this term here, the von Neumann stability analysis says that the absolute value of this term cannot be less than or equal to 1. So the just regular term here cannot be less than -1 or less than 1. So we could subtract 1 from all of this, and we can get -2 is less than or equal to, just say 2r cosine of k delta x, minus 1 is less than or equal to 0. And so we know about the cosine function that its maximum value is always going to be 1, and its minimum value is always going to be negative 1. So this term right here, if cosine was at its maximum value of 1, and we have a minus 1 right here, this value would go to 0. So the maximum value that this term here is 0. And the minimum, if this cosine function were at its minimum of negative 1 and we're subtracting another 1, the minimum value of this term is negative 2. So if we get our maximum value of 0, then this whole thing goes to 0 because it's multiplication. So we're good there. If it goes to its minimum of negative 2, we would divide this whole thing by negative 2. And we would get 1 to be greater than or equal to 2r. And so if you divide everything by 2, 1/2 has to be greater than or equal to r. So this is why if r is greater than 0.5, if it even goes to 0.501, the system will become incredibly unstable because r cannot exceed 1/2. It must be less than.